This video is part 1 of the solution to using graph and Newton-Raphson formula to obtain numerical roots. This example here has two parts. The first part, it says sketch the graph of two functions that clearly shows the equation has exactly one solution. The reason why you need to sketch two different functions is that your original equation is a combination of two items. If you're going to sketch that directly, that is possible, but a lot of people wouldn't know what the functional or graphical form of this combined function looks like. A lot of people, on the other hand, may already know what e to the minus x looks like and x cubed looks like, and then simply can just do a sketch on a coordinate space without even getting into much detail of the graph. If you're not familiar with the graphical forms of the different functions, you can always do a data table to plot the function. So safely, I would say, you want to plot a range of x, and then you want to plot the separate y's. So the first y is e to the minus x, and second y is x cubed. And then you also want to choose a range of x values, say a bit of negative, bit of positive. In some questions, you might get error out of your calculator. If you're trying to do a log, you will notice you wouldn't be able to get any values from negative side of x. That's because log functions only takes positive values. So you need a bit of basic knowledge about the domain of these functions. But for both of these functions, x can be both positive and negative. So I'm going to go with 0 in the middle and then a bit of negative on both sides. And say if I don't remember my graphical form, if I do that, I can sort of get a shape of what the graph would look like. So now I would put these values into the calculator and simply calculate what the corresponding y's are. First one, e to the minus x, when x is minus 2, you will put e to the minus 2, because x is minus 2, in the calculator. And that one is going to be e to the square. That should be about 7.4. You don't have to keep a lot of decimals because this is only a sketch. So I'm just going to write 7.4. So especially on the negative number side, you need to be careful. You're going to substitute in the value of x just into the x part, and then keep everything else exactly as it is. Otherwise, it's quite easy to make a mistake by flipping the signs in the wrong direction. So I'm going to save you guys the trouble of watch me doing the data table individually. So I'm going to pause the recording and fill the table and start recording again when I've finished filling this data table. Now, my data table is filled. I just need to plot the pairs of x, y value. So I'm going to use two different colors. I'll plot my e to the minus x in red and x cubed in a different color. So when x is minus 2, let's just put a bit of grid on here. My y value for the first graph is 7.4. So let's say this is minus 1, minus 2, 1, 2, and my biggest value here is at 8, so I'll probably go up in 2, 4, 6, 8. So it's a sketch. It doesn't have to be super exact, but you kind of need to know about where the different points are. So you want to have a reasonable representation of what the graph looks like, but it doesn't have to be graph paper level accuracy. Okay, so -2, 7.4 was -2, and go up 7.4. It's about halfway between 6 and 8. It's about there. And the next one's 2.7 -1, 2.7. So -1 from x and 2.7 on the y, so it's nearly a 3, so it's about there. And 0, 1, so 0 in the x direction and 1 in the y direction, so right there, halfway between 0 and 2. And then 1, 0.4, so it's quite low now. And then 2, 0.1, even lower, coming closer to the x-axis. And if I connect all those points in a smooth line, there's my graph for y equals e to the minus x. So some of you, a lot of you would not need to do this data graph to know that my e to the minus x is a decay function with crossing the y-axis at 1, because e to the 0's power is always going to be 1. So some of you might already know that, might not need to do the zeta table, but I'm just showing you, if you forgot what your function graph looks like, then you can use the data table to get your graph. So that's the first one. Second one, I'm going to use the green for the x cubed. So -2 is x and -8 is y. So -2 and go down. Let me write the negative side of the y-axis. -6, -8. So -2, -8 is right there. Next one, -1, -1. So -1x and -1y, it's here. And 0, 0 is the next one. And then 1, 1. So going in the positive direction now. And then 2, 8. So 2 in x, 8 up here in y. And if I connect these dots in a smooth way, I then would have my cubic graph. It's quite difficult to draw with this computer pen here, so it's just imagine I've drawn it smoothly. Now the purple graph and the turquoise graph, the blue graph, has exactly one point that they're crossing, intersecting, and that you can see actually from the graph, it's somewhere between 0 and 1. So after you've obtained this one intersection, you can conclude that the equation e to the minus x minus x3 equals 0 has exactly one solution. The rationale for that is, if your equation is this, simply by rearranging, by taking a piece onto the other side, you will obtain e to the minus x equals x to the cube. So basically left equal to right, and left is represented by this purple line, and right side is represented by this blue line. If they equal each other, that means they intersect, and when they intersect, there is your solution to this original equation when they equal each other. So that's why the graphical method works. Okay, so next video, we're gonna then use our approximated values as starting point to solve for a more accurate route using the Newton-Raphson formula. Thanks for watching.